right, good afternoon, everyone. So today we're going to continue our discussion of convolutional neural networks, and especially the convolution part. So last time we talked a bit about the idea that the early layers in a neural network essentially learn to detect some simple patterns within images, and then later layers use those as building blocks to detect more complex patterns and so on. So this pattern matching is essentially implemented through something called convolution or correlation. So basically the idea is you have a template, something like this little 4. You slide that template around your larger image, and you do a pointwise multiply between the pixels in the template and the pixels under it in the image. You sum them up, and that gives you a value. And when this image has been positioned over something that is a good match to it, you get a big value there. Whereas if this image is positioned over something here that's not a good match to it, you get a small output. So that's the idea behind correlation, essentially. That's what this is. And the equation, which is important to understand because we're going to see a more complicated version of this later today, is this one. So this shows you what happens at the output pixel indices J1 and J2. So this would be like I guess in this picture, J1 and J2 would be the location of this output, J1 and J2. And it's also the location over here. So this is J1 and J2 would be the top left corner of that box. And then the Ks here, these index over these pixels, and also they index just over these. So to find the output here at J1 and J2, we move the corner of the box there, and then using that as a starting point, we take a perturbation, K1 and K2 from that, and at all these different perturbations, we multiply top times bottom, sum them up, and we get an output. Okay, so is this equation making sense and all the different indices? Okay, good. So so as we talked about last time, if you go to the signal processing literature, this operation is called correlation. It's used a lot in things like radar, especially. And sometimes it's called convolution without flipping and reversal. But if you look at what convolution is, that's very similar, except there's some minus signs here, which means essentially you could put the minus signs there, or you could put plus signs there and put minus signs here. What it does is it essentially flips in both the top, bottom, and left to right directions this thing we call the kernel. So that's the difference between these. They're very similar, but one includes flipping and reversal. However, we don't really need this flipping and reversal for our deep networks, and so it's enough just to implement this. And even though they call these convolutional networks, they're actually implementing correlation. Just kind of a minor point. Okay, so the next thing to talk about is how we handle the boundary conditions. So when we have this template here, when we're at an edge, do I constrain the template to only be located in the image, or do I allow the template to go outside the image, and by how much? So basically there's 3 types of common ways to handle that boundary. The first one is called valid mode convolution. In that case, so let me just explain these pictures a little bit. So this would be the image, or let's say the input image. These darker blue ones, they are the kernel. So the kernel here is 3 by 3. And then this shows you the output image. Okay, so in the case on the left, in this valid mode, we are constraining the kernel so that it can never go outside the original image. It's not allowed to do something like this. As such, there's only 4 positions that it can be in, right? Those 4. And so as a result, you get a total of 4 output pixels. Okay, so every time you have it here, then you shift it to the right, you shift it down, and so on. Each time you get 1 output pixel. Is that making sense? So in this case, as you can see, as a result of the convolution, the image size changed. It got smaller. And that might not be convenient. It may not be what you want. So there's another option. It's called same mode. Actually, let's talk first about the full mode. So full mode is kind of the other extreme, where you allow the kernel to move as far off the image as you can to preserve at least 1 pixel overlap. So in this case, if we have a 3 by 3 kernel, 2 pixels will be outside the image and 1 will be in. If we had a 4 by 4 kernel, then there'd be 3 pixels outside and 1 in. And now you can see that for the same kernel and the same input image, there's a lot more locations that we can move. And this is the output image, which you can see is actually bigger than the input image. So we have one case where it got smaller, one case where it got bigger. Typically in a signal processing sort of class, when we talk about convolution or correlation, you're assuming this. But there's another option, which is to basically include just enough overlap so that the input and output images have the same size, and that is called the same mode convolution. So if you have a 3 by 3 kernel, then you allow basically the kernel to go outside the image by 1 pixel. Doing this requires that you have an odd kernel size in order to get this perfect match. Okay, so those are basically the 3 types of ways that the boundary is handled. And I would say, from what I've seen in neural networks, they usually use same mode just because it's easy to keep track of the sizes of things as you go through the network. It's easiest with this. You don't have to think about how things change as you change the kernel size. Okay. And this is just kind of a detailed example just to make sure we know how it works. So the input image, that's the light blue squares with the big digits. The kernel are these small numbers here. And this shows the output image. So when the kernel is in this position, you take like 3 times 0 plus 3 times 1 plus 2 times 2, and you sum up all those and you'll get 12. And then if you move the kernel over 1 position to the right, you repeat this 3 times 0, 2 times 1, 1 times 2, sum up all those, you get 12 again, and so on. It just shows how convolution works. And then this is valid convolution in the sense, in the sense that we don't allow this kernel to escape the image at all, and as a result, the output image is smaller than the input image. Okay, any questions on convolution, how that works, or the boundary conditions? Everybody good with this? All right. All right, so let's take a look at just some programming examples of how we do this in Python. So first we're going to do this with some Python packages, not PyTorch. And then we'll later repeat this with PyTorch and see what we need to do differently to get the same outputs. Okay, so we're going to take this famous cameraman image as the image we're going to play with. This is a grayscale image. In other words, black, white, gray, no colors. We'll talk about color images later. And this one is built into Scikit image, and so we can just get it out like this. And then the other package we need is SciPy signal for our signal processing functions. And let's look at two different applications of convolution. One will be local averaging, which you could also say is blurring. This is useful if there's a lot of noise in your image and the noise is zero mean. If you take a local average, it tends to reduce the noise because the noise averages out to zero, but it keeps the signal, although the signal gets blurred a bit. And another application will be edge detection, which we'll see also. Okay, so let's look at local averaging, and let's look at the different ways we can do the boundary conditions. So we'll make a 9 by 9 kernel, and this kernel is just going to be, you can see we're making a matrix, a 9 by 9 matrix of ones, and we're dividing by 81 so that this matrix, if you sum up all the values, you get 1. So it's just basically like an average, an averaging filter. So here's our original image. And if we, and then this is a 512 by 512 pixel image, and this is just a zoomed in version of like this corner 20 by 20 pixels. So you can see that in this corner, things are very uniformly gray. Now, let's say that we do scipy.signal.convolve2D, where we use our uniform kernel and we use full mode convolution. In this case, the output image got a little bit bigger. It's going to be 520 by 520. And if we zoom into this corner, this is what it looks like. And remember that in these images, black is 0, white is 1, the largest pixel. And so when we did our convolution and we allowed our kernel to go outside our image, we assumed that outside here was all zeros. In other words, we're assuming that it was all black there. And so as a result, especially when our kernel is just here at the corner, we're basically averaging a lot of black with one gray pixel. And as you can see, the output of that is almost totally black. So the result of this full mode convolution is that the more the kernel is outside the image, the darker this edge becomes. So these are the effects of assuming that you have zeros around your image. As you can see, it's maybe not really accurate to do so because in fact the true image didn't have zeros there, it was gray there. So there's sort of a cost by making an assumption like that. You get some weird effects. And this, you can see this happens all around the edge of the image. You get this black region. Okay, so what about, let's do the valid mode next. So in valid mode, we don't allow our kernel to escape the image at all, and as a result, it's perfectly gray out here, just like the original. That's good, but the image has shrunk a little bit now to 504 by 504. So we have this compromise. The same mode convolution will give us a 512 by 512 image where we have a little bit of these boundary effects, but not nearly as bad as that. Okay, so it's just demonstration of what happens when we slide around a little averaging filter through here. And the other thing we see happening is these images are all going to be the same on the inside, but they're all just a bit blurry compared to the original, right? This is because we have a 9 by 9 averaging filter that we move around that just takes the average of 9 pixels, or actually 81 pixels. And as you can see, when you take that average, everything gets kind of blurry. So if there was noise here, there's no noise in this image, but if there was noise, probably the output image would look a lot less noisy, but at the compromise of being a little bit blurred. Okay, any questions on anything here? All right. So we can also play with the kernel size. We can go from 9 by 9 to 15 by 15. And you can see the larger the kernel is, the more averaging we do, the more blurry things get. We can also play with different shapes for the kernel. So rather than using a uniform average filter, we could have a filter that weights the pixels in the center more than the pixels on the outside. And we can do that with a two-dimensional Gaussian shape. So this is a Gaussian blur kernel. And what this is going to do is it's going to reduce blurriness a little bit. So this is a uniform kernel 9 by 9 and the Gaussian 9 by 9. And you can see that the Gaussian is a little bit sharper. So just different options that people use. We'll play with this Gaussian filter a little bit more later. All right, so here's a little bit more of an interesting application called edge detection. So here we want to detect edges in our image, and these are going to be vertical or horizontal edges. So let me just show you first what the results look like, and then we can talk about them. So if I want to find vertical edges, as you can see, that is what we did here. So any kind of vertical shapes you can see are picked up, but any horizontal edges like these are essentially gone, right? So, and like this edge here is not picked up. So this is picking up vertical edges, and then this one on the right is picking up horizontal edges. So it's picking up this stuff, but like this vertical thing here is missing entirely. Okay, so this is a real application, sometimes detecting edges in images, and as we'll see, it's really easy to do this with convolution. So, so the way we do this is we construct the kernels this way, and this is just one choice, but it's a pretty well-known choice called the Sobel filter. And so this here would be appropriate for detecting vertical edges. So what you see here is that the first column is all positive, the second column is all negative, and the middle column is 0. So if there's an edge, let's say you go from, say your image is dark on this side and light on this side. Remember that dark means small numbers, light means big numbers, and you correlate with this filter, then what you'll see is that the big numbers get negative, the small numbers get positive, and as a result, there's more or less a decrease because the big numbers are negative. So when the output of this is negative for correlation, that would signify the presence of a vertical edge. Now, when we do convolution, we have to remember that this thing gets flipped. So basically the negatives go here and the positives go on the other side. So essentially what happens is when you go from dark to light versus light to dark, you get either positive or negative. This is the one for vertical edges, and then this would be the one for horizontal edges. We could have also done like 2, 2, 2, 2 like this, but this has sort of more of a gradual onset, similar to that Gaussian shape, which is going to use pixels in the middle of this more than on the edges. So that's how these work. And so we can construct these just by, hard coding these values into our kernels, doing our convolution. And if you look at, going from, let's say, light to dark, you get a black edge. And if you go from dark to light, like here, you get a light edge. So, and this works just as we predicted it would. And then convolution versus correlation, because one of them has flipping and reversal, essentially what you see as a dark edge here turns light, in both cases dark, light. Okay, so that's edge detection. Another thing you can do with convolution, and as we see when we look at what was actually learned in AlexNet, that neural network, we'll see examples of these Sobel-like filters being learned and being the building blocks of the building blocks of these convolutional neural networks. Okay, so coming back to convolutional neural networks now that we know a little bit more about convolution and so on, we can talk about how these networks are constructed. So one thing to remember when looking at these pictures is that the blue things here, these are actually the data representations. These are not like blocks, like system blocks. These are signal blocks, data blocks. And the layers on the network are really represented in this case by these pyramid things and by the arrows. So those are doing the processing. Okay, so when we look at the very beginning, we see that we have 224 by 224 by 3. So this is because ImageNet has 224 by 224 images with red, green, blue color channels. So there's basically 3 channels, 24 by 224. Okay, so that's where we start. Then there's a convolutional layer that uses a kernel of 11 by 11. And basically, as we know, the way convolution works is you can think of this as like a little pattern. You slide that kernel around to all the different locations of that image, and then as a result, you get outputs over here. Now the thing is, there's not just one channel here and one channel here like we saw with our cameraman image. There's actually 3 channels here and 96 channels here. So these are this 96 is a design decision. They probably tried different numbers and they found the 96 worked well. And so it turns out that for each combination of input and output channel, you need a separate kernel. So that's how it works. You will learn a separate kernel from each of these 3 to each of these 96. So in total, 3 times 96 different 11 by 11 kernels were learned for this first layer. So we'll talk a little bit more about the exact equation that's used in a moment, but that's one thing to note. Another thing you can note is that somehow this number of pixels also changed. It went from 224 by 224 to 55 by 55. So this is another thing that you see architecturally going on in these networks, is you start out with something that's the size of the number of image pixels, but as you go through the network, remember that these are classification networks, in this case to classify 1,000 examples, so you somehow want to morph the input data, which is a pixel image, to output, which is not an image at all. It's a vector of class probabilities. So somehow you have to translate between these sizes to these sizes. And you can see this is sort of gradually done, where as you go through the network, you use less and less pixels to represent things, but more and more channels. And eventually, at some point, and we'll talk about this in more detail later, but at some point, you essentially flatten or just string all those numbers together in one long vector, and then you use dense layers. So you're gradually going from the pixel domain to the class domain. Okay, so how do we get this reduction here from 224 to 55? We do subsampling or pooling. These are just ways to reduce the number of pixels, and typically they do so by an integer number. Like, for example, if we subsampled by 4 in each of these dimensions, that would get us down to what would be 56, right? And so this is 55, and that might be because we have to look at the code, but maybe they used maybe they used valid mode, which would also make things a little bit smaller. So in any case, there's more or less a reduction of 4 in every dimension, in both dimensions here. And then going from here to here, there's another reduction by a factor of 2, and then here to here, another by a factor of 2. So we'll talk in more detail about these in the future. But so overall, what you see here in each of these convolutional layers is there's 2D convolution with several kernels. Then there's activation, things like ReLU, and then there's these data reduction strategies, pixel domain reduction strategies like subsampling or pooling. So that happens in each one of these. And then finally you get to this point where you just unravel this into one long vector of 4096 samples. And then these layers are exactly like the ones from the last unit. So this is basically multi-layer perceptron. In this case, a 3-layer network. And this one ends up with 1,000 because we're doing 1,000-way classification. Okay, so this is the overall structure you tend to see in these convolutional neural networks.
So like channels usually represent the color, like RGB. So right now,
In the input image, they're RGB, but then in the first layer already, they're no longer RGB. There's 96 of these things.
is that information still present somewhere, like the channel information in the original image, or is it?
No, it's like you're making a whole bunch of different kernels, and so each kernel that you're learning is taking one of these channels to one of these channels. So by allowing more channels in this stage of the network, you're just allowing your network to learn different things. In the same way that, remember how when we designed these MLPs, we had to choose how many channels to use for the hidden layers, right? And we said basically if we use too many channels, maybe it's overfitting. If we use too few channels, the network can't learn what it needs to learn in order to get the job done. So it's a little bit similar here. We have to choose these numbers wisely. If we choose them way too big, we end up having way too many coefficients to learn, because the number of learnable coefficients is directly proportional to the number of hidden channels here. So I have more things to learn as I increase that. That's bad. But if I decrease it too much, then the network can't learn as many different things that it needs to learn to classify these 1,000 classes well. So there's no magic number or magic equation. It really depends on the data set, the task at hand, how difficult the classes are to separate all those things. And for the ImageNet data set, these people came up with these numbers at the end. And it also has to do with the compute power you have. As these things get bigger, they become harder to train, longer to train. So at the time, these are the numbers they settle on, probably after a lot of experimentation. I'll show you exactly what these kernels look like later, if not today, in the next lecture. Okay, so other questions about overall look of these networks? Okay. So let's talk a little bit more about these things. These things are called tensors in general. Tensors are just multidimensional arrays. It's just a word for multidimensional array. So these here are what we call 3-way tensors. They're 3-dimensional arrays. A matrix is a 2-way tensor. A vector is a 1-way tensor. But it turns out that in PyTorch, the main, at least when you work with images, the main quantity you have is a 4-way tensor. And it has to be built exactly like this. Otherwise, PyTorch doesn't know what you're doing. So the first is your batch index. The second is your channel index. The next is your height. The next is the width. So even though these are represented here as, they look like 3-way tensors, in actuality, you have one of these guys for every element in your batch. And so that makes it a 4-way tensor. So there's actually 4-way tensors propagating through the network. Okay, and they always have this structure. Now, when you work with skimage, like we did with the cameraman, it wants a different format. So when you work with, let's say, RGB images, then you want height, you want 3-way tensors of height, width, and then the next one is a channel index. So 3 channels in this case, and they're in the order of red, green, blue. So that means when you go between PyTorch and skimage, you need to do some conversions. You need to convert from one representation to another and back, and it'll show you how to do that. Of course, if you're working with a grayscale image like the one we saw, like the cameraman, that's just a matrix of brightnesses, height by width. Okay, so these are all examples of tensors for different applications or different frameworks. Okay, so some terminology here. The number of dimensions in a tensor sometimes is called the degree of the tensor or the order of the tensor or the rank. You have to be a little careful. Remember when we talk about matrices and you talk about the rank of a matrix, that has a very specific meaning about number of linearly independent columns or rows. When you talk about tensors, rank is completely different. So the shape of a tensor tells you how many elements you have along each dimension. So if I have a tensor, a 3-way tensor that's 10 by 20 by 4, you would say the shape is 1024 and degree is 3. So that's probably familiar to you from using NumPy or PyTorch. When you do the numpy.shape or np shape of an ND array, then it gives you this list of numbers. It shows you the dimensions, right? And tensors are things you have been using. They're basic data types in PyTorch and Python, like ND arrays and NumPy and torch tensors. Okay. So now we can talk much more specifically about what those convolutional layers do. So we're going to think about our weight tensor as this 4-way tensor with this shape. This is the number of output channels, the number of input channels, the number of vertical pixels, and the number of horizontal pixels. Okay, so when we talk about that first layer here, number of input channels is 3, number of output channels is 96, and we have 11 by 11 pixels. Okay, so those would be those 4 numbers here. So that's, this weight tensor is what we use to do the convolution, but then similar to things we've seen before, we might also want to have a bias vector, just a shift. And in this case, for these convolutional layers, you just use one single shift for every channel, one scalar shift per channel. So this bias vector, or intercept vector, is just a vector with cout elements. So this, below here, this is finally the equation of a convolutional layer, so it's very important. Looks a little complicated, so let's try to work our way through this. So similar to convolution, we see the kernel here, we see the input signal here, the output signal here. Okay, now one little difference is you can see we're adding a bias, and this is for output channel M. You can see that we use a different bias. So again, this is, sorry, so this shape here corresponds to the kernel. And then this one, remember, this is batch, output channel, vertical pixel, horizontal pixel. Okay, so this is saying if you look at the ith image in the batch, you can see that the weights have nothing to do with the batch image. In other words, the same weights are used for every index into the batch. And the batch index only appears here, so the ith input image leads to the ith output image. So the batch index is pretty easy to understand how that works. Of course, there's no batch image there. If you look at the spatial indices, the spatial indices work exactly like the simple convolution equation that we saw before. Okay, so this is J1, J2 are our output indices, and those sort of are the anchors, and then K1, K2 they go through the kernel and they do that pattern matching thing we saw before. Okay, so hopefully you can recognize that. So really the only thing more to talk about is, and maybe I'll highlight it, is how the channels work. Okay, the channels work a lot like matrix multiplication. So if you think about matrix multiplication, you would have something like the output. So if I'm doing a vector Z is vector W, or sorry, matrix W times vector A, you would write you'd write matrix multiplication like this, right? So we have output index M, input index N, and then the matrix W uses indices M and N. So when you look at that, that is exactly what's happening here. So there's our sum. Okay, so this is really a combination between convolution and matrix multiplication, sort of a hybrid. But I think the easiest way to describe it is in the sentence. So for each output channel M, we correlate each input channel N using this specific kernel. So the kernel here, this is a 2D kernel specific to output M and input N. And then we just sum that across the N input channels. That's what this does. Maybe I'll highlight that green. Okay, so this is how convolutional layers work. There's a separate kernel for every input-output channel pair that is applied, and then finally there's just, for each output channel, you sum those across all the input channels, the outputs of the convolutions. So, does it make sense, or is it confusing? Yeah.
What is I?
Batch. I is a batch index. So I have a bunch of images in a batch, as we know, and basically I'm doing the same thing to every batch element. I'm multiplying by W and adding a bias. Some other questions? I know this is a little bit tricky the first time you see it. No questions? Making sense or just impenetrable? Processing. Okay. Okay. Well, so that's what happens in convolution. After we do convolution, we just put it through our ReLU or whatever activation we're using, and then now we can talk about how we reduce the dimensions in the pixel space using subsampling or pooling. So subsampling is maybe the easiest to talk about. So essentially, one way to think about it is you have an output image. You break this into little blocks of S by S dimensions, S by S pixels. And within each one of those blocks, all you do is you keep the top left, throw away all the other things. So S is called the stride here. You can say it's how far you move this little box vertically and horizontally as you move it through. And as you can see, if you keep only those red dots, you're keeping 1 over S squared of your pixels, right? Throwing all the rest away. Okay, so that's what plain subsampling does. Keep only the top left pixel of every S by S region. So if you're suspicious of this, it makes sense because you're just throwing out all this other information. So why do we keep the top left one? Why not some other one? So there are other options. There is max pooling, which is a little more sophisticated. It says, I'm going to look through each one of these little images and find the maximum pixel and keep that one. So that way, the little red dot moves around every time and keeps the max. Also, you can be a little bit more flexible. You can have the stride separate from the size of the region that you look for the max over. So let me show you how this works. So imagine that this is my input image. These are the pixel values. And I want to do max pooling with a stride of 2 and with, this is like K by K, where K is 2 little filters. So that means the K basically tells us how big do I do my maximization over, and the stride says how far do you shift it each time. So if I'm doing 2 by 2, I do a search over this, so that 5 would be the biggest. That's the one I'm going to keep here. In this one, I do a search, I find 4 is the biggest, so that's the one I keep there. Here, 4 is the biggest again, and so on. Now, let's say that I wanted to do K equals 3. So now I'm going to search over a 3 by 3 region, but I'm still going to shift by 2. So I do my search over this. It still ends up that 5 is the biggest. And then over here, I'm going to do another search over this. In this case, it still appears that 4 is the biggest, but you can see the difference. Here it's a 2 by 2 search. Here's a 3 by 3 search. But in both cases, you shift by 2 every time. So this is another option. It's pretty popular. And then the third one is average pooling, which instead of taking the max, you just take the average. In signal processing terminology, this last thing, average pooling, we call this decimation, basically. And subsampling, we would call downsampling. Subsampling can be made very fast because since we know which pixel we're going to keep, we can be smart. When we do the convolution, we don't even compute the other ones. Because why should we compute all these other things if we're going to throw them away? Okay, so when you implement subsampling, it's actually implemented as part of convolution. It's not a separate thing you do. You just tell your convolutional layer, I want to do subsampling with a given stride, and then it does it in a smart way. On the other hand, max pooling and average pooling, the only way to do that is you compute all the convolutional outputs, and then after that, you either look through them to find the max or you compute the average. So in terms of the implementation, this is going to be much more expensive than subsampling. So I believe in AlexNet because, so in AlexNet, especially in 10 years ago, hardware was not where it was today. They didn't have GPUs to do machine learning in those days. There was no special purpose GPU market. So they used downsampling with the stride of 4. In later layers, they used max pooling. But that initial one, they used downsampling. So that cut down on the number of operations. Okay. So all this stuff is performed independently on every channel and every item in the batch. Okay. And this is how, essentially, if you didn't do this, again, we want to convert from these really big images to essentially something that you could say is like a 1 pixel image, but with many, many channels, with like 4096 channels. So we want to do this gradual transformation. And we do this by gradually shrinking our image size and growing our channel size. And so to shrink our image size, we need, we use subsampling or pooling. If we didn't do that, what would happen is we would have these giant images through the network, and we would keep growing their channels, and pretty soon we just would run out of memory. We wouldn't be able to store all this stuff. So it's like we're just basically changing the shape of this thing as we go through. Okay, so that's subsampling and pooling. Any questions on those? Okay. And then what about dense layers? So we mostly talked about these, but let me be a little bit explicit here. So suppose that right before our first dense layer, we have our last convolutional layer, and that convolutional layer, let's say that it had an output tensor of this size. So there's B elements in our batch, C out channels, and we have N1 by N2 pixels, let's just say. So before we get to our first dense layer, for each batch item, we basically take this three-way tensor and we just flatten it, meaning we turn it into one big long vector. And so now we go from a four-way tensor to a two-way tensor, where the first indexes across the elements in the batch, and the second is just however many pixels you get from this product. Okay, so that's what this flattening is, just a reshaping. And then once we have that reshaped, this is the same equation. This is just a matrix multiply. This is a separate matrix multiply for every batch item, I, but otherwise it's just M is your output index, N is your input index. This is a matrix of N out by N in, and then you have your bias. So this is exactly what we did in the last unit. If you want to connect this to convolutional kernels, you could say that, or convolutional layers, if you have a convolutional layer with a 1-by-1 kernel, so the thing you're sliding around just has one pixel, and if your input and output, and if your images also have one pixel, then essentially you have a dense layer. So the dense layer is different from a convolutional layer anytime the convolutional layer has either a kernel that's bigger than 1-by-1 or an image that's bigger than 1-by-1 pixel. Okay. And so now you might ask, why do we use convolution? Could we just use dense layers everywhere? I hope to convince you that dense layers have way more parameters than convolutional layers. So convolutional layers, way fewer parameters to learn. So let's just do an example by looking at what happens with AlexNet. And let's look at the second layer of AlexNet. So we don't need to really worry about how big the batch is. It's not important. In AlexNet's second layer, we have an input that has 96 channels, output that has 256 channels, and we go from 55, and we have 55 by 55 images on input and output. So let's see how many weights and biases we need to learn for a convolutional layer. So remember, like for a convolutional layer, each kernel we learn has K1 times K2, where in AlexNet's second layer, K is 5. Okay, so that's for each kernel, each 2D kernel we learn, but we have to learn a separate kernel for every input-output channel pair. So the total number of kernels is C out times C in, and then this many numbers per kernel. So when you plug all these numbers in, you get 600,000 weights to learn just for that layer. Sounds like a lot, but let's look at what happened if we instead used fully connected layer instead. So for a fully connected layer, we have to look at the total number of input pixels and the total number of output pixels. So total number of input pixels will be C in times 55 times 55. So that will be the input dimension. The output dimension will be those numbers multiplied together. And then finally, the matrix that we need, if you think if I have a vector, right, this vector has, in this case, C out times N1 times N2, this vector has Cn times n1 times n2. That means the matrix is, the number of coefficients of the matrix is the product of the lengths. So that's C out times Cn times n1 squared times n2 squared. When you plug all those numbers in together, you find that it has 200 billion weights. So there's no way you could ever do that. So there's a huge reduction by basically on the order of a factor of 1,000,000 in terms of the parameters consumed by a convolutional layer versus a fully connected layer. So fully connected layers, you just simply can't use them in early stages. They would be way too giant. But yes, you can do convolutional layers. The other thing that we know about convolutional layers that we like is they exploit translational invariance. They learn these small local patterns that we can use as building blocks to learn later local patterns and so on. If you could somehow implement fully connected layers, in theory, they could learn what a convolutional layer could learn because they can learn that and much more. But there's a lot more parameters, and so with a limited data size, due to overfitting, you might never learn the same thing. So at least in these early networks like AlexNet, the final layers did use dense layers. So the number of dense layers you use here is really a design parameter. In these early days, they used 3, which was kind of a lot. In later days, like I think the more current networks will just use 1 dense layer. I'll use convolutional all the way till the end. So this is just a design parameter, and somehow in those early days they thought, they needed more dense layers. Okay, and you could say it makes sense to use a dense layer at least in the end because you always have to have a fixed number of classes, right? 1,000 classes in this case. No matter what the input size is, you need 1,000 classes. So you don't want something, if you use all convolutional layers and you change the number of input pixels, you will also change the size of that last representation, and that doesn't really make sense. It has to be 1,000 no matter what size image. So, so there's a little bit about why we use convolution. Good? All right. Okay, so we can talk a little bit about how we do this stuff in PyTorch. So we saw that we were able to do edge detection in SciPy. These are the filters we want to implement. Let's see how we do this in PyTorch. So we're going to use the cameraman again. But the thing we have to remember is that in order to work with PyTorch, we have to get everything into the framework that PyTorch wants. So remember, PyTorch wants something of a 4-way tensor. The dimension of the first dimension of that tensor is the number of images per batch. In this case, we just have a single image we're working with. So say our batch size is 1. Second, it wants to know how many channels in the image. Well, this is a grayscale image, so there's only 1 channel. If it was color, there'd be 3. And then the dimensions of the image, 512 by 512. So we can basically just set number of images to 1, number of input channels to 1. We make this batch shape, which is this vector of numbers, 1, 1, 512, 5, 512. And then we just do im.reshape. And what that does is it just sort of adds these ghost dimensions here. It's not really changing the data at all. It's just changing the accounting of that data. Finally, this is in NumPy, so we convert it to a torch tensor. And now it has the right dimensions for PyTorch to work with it. Okay, so how do we create these convolutional layers? So these are what we want our convolution. We want to make basically 2 kernels. One is going to be our Sobel in the X direction, the others are Sobel kernel in the Y direction. So we can think about this as a convolutional layer that takes in one channel and gives us a two-channel image. One will be the vertical and the other will be the horizontal edge channels. So we have input channels equals 1, output channels equals 2. The kernel size, that's going to be these 3x3 kernels. And we do this with, this is the neural network library in PyTorch, conv2D, two-dimensional convolution. If you're working with 1D signals, you would want to use one-dimensional convolution. If you're working with volumes, three-dimensional signals, you would want to use 3D convolution. So you just want to match the convolution to the signal size. Okay, so we know the coefficients we want to use. The way to handle them is first, once we created this model, what happens is PyTorch initializes the weights randomly. So what we're going to do is we're going to pull out the kernel tensor W as well as the bias vector. We do this by doing the state dictionary. So now we have these things available to us. Then we're going to overwrite what's in them by the torch tensors of these things. So we pull them out, we overwrite them, and then we load them back in like this. And so we overwrite them in the state dictionary structure, and then we do model load state dictionary, and we get it in. Then since our signal has been put in the right format, we just put it through our model, which is this 2D convolutional layer. We get out our Y-torch, and now we just have to detach it to NumPy. Okay, and when we plot the two, we can now extract channel 0 and channel 1. You can see here we just index the channel we want, and then we plot them, and you can see these are exactly what we got from scipy.signal.correlate2D. So it did the job we want. And even though it's called a convolutional layer, it's really doing correlation. Okay, so the next demonstration is a little bit more sophisticated. What we're going to do is we're going to take a 3-color image, and we're going to put it through 4 different convolutional filters that have the goal. This one, so we're going to get out a 4-channel image. The first channel, essentially, we want to extract the sort of like a red subimage of this, extract a green one, a blue one, and a pink one. So this is going to try to filter out, or it's try to preserve red content, green content, blue, and pink. And let me just show you the outputs. So the output of this is going to be a 4-channel image. And so as humans, it's hard for us to visualize 4 colors. So we can't show you that way, but we can extract 4 grayscale images and look at them separately. And as you can see, this one did a good job of, like where this is white, that means it has the most brightness, the most content. That was the orange. The orange color matched this best. And then over here, this green color was matched best by those apples. So they end up being brightest. And then the blue color ends up being matched most in those things. Those things have blue in it. Maybe if you're like a painter, you would know how to mix your colors. You'd be like, oh yeah, I can see there's a lot of blue in here. And then the pink was, there's mostly pink in there. So this is showing what we're trying to do. And then I don't have enough time today to show you the details, but in the next lecture, I'll show you how we can do all this. We're going to have to do a little bit of conversion from the SK image format to PyTorch. Then we're going to have to figure out how to construct our 4-way convolutional kernel, tensor, and all that. Let's see. So then the other announcement I have is I'm going to be out of town next Monday and Wednesday. So unfortunately, I won't be here to lecture. I will pre-record at least 1 lecture or 2 I think we're maybe a day ahead of schedule, so I might be able to just do one. But I apologize, I won't be here. So please don't come to class Wednesday or Monday next week, but I'll be back on Friday, and I'll see you guys then.